So this year our project, what we're doing is we're taking Shearwind's idea of a wind catcher that is able to reduce the startup speed of a wind turbine, shrinking it down to a smaller scale, one, to prove that it works, and two, making it replicable for other high schools. The other part of the project is taking the Nanoline, embedding the Nanoline into this idea of a wind catcher, and again, making that fully functional off the Nanoline and it being able to be used by other high schools.
For the design of our project, we decided to make a inverted hyperbola revolve around a central axis. So that gives us a funnel-looking object that will capture the wind. The wind will go in right here. And then the next funnel is down here. The wind will carry down and around. And then we're going to have a Venturi effect to speed up the wind to our turbine, and we'll get our wind speed from there, and it will be power generated.
So this is our funnel for this year, and we designed this out of old wood from Michael's old speaker. So we're reusing, Green Power Club right here. We got to get the recycling. But anyway, just built it, cut some nice 36-degree angles to make pentagons, and it's going to be a nice funnel.
The idea for this year's project was to embed the Nanoline into newly emerging alternative energy. Now, there are three parts to our project. One is power production, two is the use and monitoring of that power, and three is the directing of the power. Now, we'll be using the Nanoline to direct the power and to monitor and use it. In order to direct it, we will have two set modes. The first of which is demonstration mode. When we have the wind going to our project and it's producing power, we will have a set bar graph that lights up to the correct percentage of what we're producing. Now this is demonstration mode. Application mode, which is our second mode, will be where we actually use this power. And in order to do that, we will have all of the power going to our batteries, and those batteries will be then connected to an iPhone, which will be directly charged off of them. Now, we have the monitoring of the power. We will be using the Nanoline for this as well, and it will be reading the voltage of what we're producing and sending that information to our iPad. There we will correlate it to the correct ampage and power that is being produced, and relate that to the wind speed off of what's being gathered. this is our project thus far. We are emphasizing how the Nanoline can be used to help make power distribution, monitoring, and usage easier for a power plant or power producer by using an easier human-machine interface, and while we're doing so, we're going to demonstrate the efficiency of new technology as opposed to traditional. Okay, so this is the new technology. It is called a Venturi, and what it does is it funnels the air coming in to a smaller point, and thus increasing the force presented on the turbine, spinning the turbine faster and allowing it to produce more power. This is what we're using as a traditional, because you can tell it's using propeller blades that catch the air on using the propeller instead of concentrating it to a single point like our Venturi. The way that we're going to demonstrate the power is we have a set of LED lights right here, and as power is increased, we have one set for the traditional and one set for the Venturi. This is Venturi and this is traditional, and as power increases, you'll see the lights light up more and brighter. We also wanted to show that we could apply this power in a practical sense, so we decided that we will be charging a cellular phone because it's commonly used and it's a good thing to charge. And to make it easier for a person to use, we decided to go with an iPad so we can monitor how much power is being produced by the green wind, which is what our Venturi is, the traditional turbine. And in order to maintain, a very important thing is, in our system we're using batteries, so we want to make sure we can tell what our battery levels at all times. On our program we also have shown the outputs for the lights, and that is to be able to tell if we're in demo mode what lights are on if we're not able to actually see them. I'm about to demonstrate the traditional turbine. So on the iPad, on our graph, you'll see the green line start to make a peak, and it should peak around 2,000, maybe 1,500, because this is our scale that we're using as of right now. And this is reading voltage. Also, our lights, they probably won't even turn on because it's not producing that much power. Now that's the first step. Now I put it on high power. That was the first one. The first peak was on half power, and the second peak you saw was on high power, and that is the max that the traditional turbine is able to put out because it can't spin as fast. Now I'm going to demonstrate the Venturi, and you should see the peak go all the way up to 4,000, or a little bit above, on high power, and it should peak on half power right around where the traditional turbine maxed out at. So this is half power. Okay, that demonstrates our graph how much Venturi can actually increase the power production, because they're both the same motor, and one can obviously produce more power than the other. This is what we call app mode, and as you can see, our station is charging our phone using our system solely. The project this year is definitely about power control. We want to understand how to distribute, monitor, or use that power we're creating. But I would like to thank you for giving us this opportunity to learn about all this new technology and experience it firsthand.